Now, based on the last concept, here I am giving a question based on the rate of reaction. For the following reaction, 2SO2 plus O2 is gives rise to 2SO3. For this reaction, they have given they have given the appearance of sulfur trioxide. That means the rate of formation they have given for this reaction, the rate of formation the rate of formation of sulfur trioxide. For this reaction, the rate of formation of sulfur trioxide is 100 grams per minute. 100 grams per minute. Hence hence the rate of the rate of disappearance of the rate of disappearance of the rate of disappearance of oxygen is, right. This is what the question, and they have given the options like 40 gram per minute, 40 gram per minute. Second option they have given 20 gram per minute. Third option they have given 100 gram per minute. Fourth option they have given 80 gram per minute. So now let's check the correct option by solving this question. Clear. Now how to solve this kind of questions? Here, based on the reaction 2SO2 plus O2 gives rise to 2SO3. For this reaction, they have given sulfur trioxide amount, the rate of formation of sulfur trioxide expressed in terms of grams per minute. Clear. So the amount of sulfur trioxide they have given. Now we need to calculate the rate of disappearance of oxygen. So now, as per the equation for this reaction, I am writing once again the reaction 2SO2 plus O2 is gives rise to 2SO3. For this reaction, I am writing the rate of reaction, that is minus 1 by 2 delta of SO2 by delta T is equal to minus of delta O2 by delta T is equal to plus 1 by 2 delta SO3 by delta T, right. We know how to calculate the how to write the rate of reactions. Clear. Now based on this data they are asking about that the disappearance of oxygen and given data about the sulfur trioxide. Now by equalizing these two, we need to solve the numerical. So based on this, the concentration of oxygen we have to first of all calculate based on the amount of sulfur trioxide. So here we need to convert this amount of sulfur trioxide. They have given amount of sulfur trioxide is formed 100 grams per minute, right. So amount of sulfur trioxide, that means mass of sulfur trioxide they have given. Mass of sulfur trioxide they have given 100 gram per minute. So we have to calculate into concentration. That means number of moles we have to calculate. So number of moles equal to, we know that mass by molar mass, right. So here mass is given 100 by molar mass of sulfur trioxide we need to calculate, right. We know that mass of sulfur will be 32 grams and here each oxygen will be 16 grams. So therefore here 3 oxygens will be there. 16 3s are 48 and total by adding these two we will get 80 grams. Clear. So therefore molar mass of sulfur trioxide will be 80. So therefore we will get here 5 by 4 moles. Clear. The concentration will be 5 by 4. So now by equalizing this we have to calculate the disappearance of oxygen, right. Delta T equal to, we have got 1 by 2 into the sulfur trioxide we have converted into moles. Concentration we have converted the number of moles into concentration. We have converted the mass of sulfur trioxide into concentration. So therefore 1 by 2 into 5 by 4. Clear. Number of moles. Clear. Now based on this we have to simplify here. Minus delta O2 by delta T, concentration of O2 equal to, we have got 5 by 8, but this is what concentration, Once again, the question is asking in terms of mass. So we have to convert this concentration into mass by using mass by molar mass. Clear? Now upon simplifying, we know that mass of oxygen we have to calculate, the disappearance of oxygen we have to calculate in terms of mass by molar mass of oxygen will be 32. So therefore 5 by 8, that is equal to 5 by 8. Upon simplifying, we will get the mass of oxygen. That means here we will get 5 by 8 into 32. Clear? So 8 ones are 8 fours are, therefore we will get the answer will be 20 grams per minute. Clear? So therefore we'll check the option which is correct. Clear? So answer will be the second option, 20 grams per minute is the correct answer. Clear? Next we are going to discussing about the affecting factors. Affecting factors of affecting factors of rate of reaction. Affecting factors of rate of reaction. So here the rate of reaction can be influenced by various factors. We will discuss here one by one. Clear? So first of all I am using the affecting factor, that is concentration. So what will happen in a reaction if we increase the concentration of reactants? Clear? So the rate of reaction will be increase or decrease. Let's check by taking a simple reaction. Suppose example I have considered a reaction A is gives rise to B, right? Suppose initially I have taken 5 moles per liter, that means 5 molarity of A, 5 moles per liter I have taken of A, and same reactant A is converted into some B. Here I have taken 10 moles per liter, that means 10 molarity. So here I have taken concentration in initially 5 molarity, and here I have taken in the second place as 10 molarity. So therefore here if you observe here from case 1 to case 2, I have increased the concentration from 5 molarity to 10 molarity, right? Now what will happen during the changing the concentration of the reactant? Let's observe here in the process. Now here initially I have taken 5 moles per liter. Suppose example 5 moles per liter. Suppose 5 moles per liter I have taken in a container, right? At that time, suppose imagine some 20 collisions will be occurred during in the reaction process. Similarly, I have taken in a container with 10 moles per liter, right? One is in 5 molarity, nothing but 5 moles per liter. Another container I have taken 10 molarity, that means 10 moles per liter. So at that time here, while upon increasing the concentration, obviously number of collisions between the particles will be increases. Imagine here in 5 molarity 20 collisions, now here in 10 molarity obviously number of collisions will be increases, right? So therefore number of collisions increases, then rate of formation of product will be increases, right? That means the formation of product depends upon the collisions. Number of moles or the rate of formation of product will be depends upon the collisions occurs between the reactant molecules. So obviously concentration increases, number of collisions will be increases. So once the number of collisions increases, the rate of formation of product also will be increases. At the same time, that result can also be observed by decreasing in the both cases. So by decreasing, we have observed that the number of collisions obviously decreases. So therefore, based on that number of collisions, here we are writing that a rate of reaction is directly proportional to number of collisions. And we will completely detailedly we will discuss in collision theory what kind of collisions will be there, right? Is there any effective collision or ineffective collision, right? So generally here discussing about the collisions, right? So here rate of reaction increases, concentration increases, that means number of collisions increases, then rate of reaction will be increases. That means rate of reaction is directly proportional to concentration. If we increase the concentration, rate of reaction get increased. If we decrease the concentration, rate of reaction will be get decreased. So therefore we got the relation as directly proportional because of the number of collisions, effective collisions are increasing. All right. Now, based on that, I am writing here rate of a reaction is directly proportional to concentration of reactants. Clear? Now, for any balanced reaction, suppose example here I am writing the concentration relation with respect to rate of reaction. So I can write this expression as like rate of reaction directly proportional to concentration of reactant. Here the reactant is A. Suppose I have taken another reaction like this, 2A is gives rise to B. The rate of reaction is observed like this when the stoichiometric coefficients are raised to be its power. And this the relation which is expressed about the concentration versus rate of reaction is known as law of mass action. Law of mass action, or it is also called as rate law. Rate law, where the rate law is nothing but which gives the relation between the concentration versus rate of reaction. So whenever this coefficient is getting changed, obviously the rate of reaction also will be get changed. So that depends upon the rate of reaction depends upon the stoichiometric coefficient as well. So generally for any reaction, suppose example I have taken XA plus YB is gives rise to MC plus ND, where already I have explained in the last class, where XY are stoichiometric coefficients of reactants, right? And where M and N are stoichiometric coefficients of products. Clear? Where AB are reactants, C and D are products. Clear? AB are reactants, CD are products. Now according to this reaction, the relation I am going to writing according to the rate law, rate of any reaction is directly proportional to concentration of reactant. Here the reactants are A and B. So therefore I am writing the concentration of A and the concentration of B. When the stoichiometric coefficients are given like here X and Y, that can be raised to be as its powers. Clear? So hence this expression is indicates the rate of reaction as per the concentration factor. Clear? And hence this is also called as rate law for this reaction. Clear? So as per the law of mass action, the concentration increases, rate of reaction also will be get increases. Now during in the process, if we remove the proportionality symbol, we'll get a constant. Obviously the brand ambassador for constant is K, right? So K into A power X into B power Y. So here where K is called as rate constant or specific rate, or it is also called specific rate. It's a very important. Here there are many questions will be there based on the rate constant and the rate law. Clear? And whereas in this rate law, the sum of the powers, the sum of the powers for this reaction is called order of the reaction. Very important. The order of the reaction is that the sum of the powers of the concentration terms of the reactant as per the rate law. Clear? Is called order of the reaction. Here we have got two new terms. One is rate constant, another one is order of the reaction. Now suppose if the order of the reaction is 1, order of the reaction is 1. Suppose example I am taking A is gives rise to B as per the rate law. Suppose example this is the rate law, right? So here the order is 1. Here the order is 1 because the sum of the powers of the concentration of the reactant, here only 1 will be there. So here I am assuming order is X as 1. Clear? So generally order is denoted by N here as per the books, we have to take the order with the letter n. So here order is the 1. Suppose example, I have taken a reaction like this. For the experimental law, experimental data reveals that R equal to K into A square. Hence here the order of the reaction is 2. Suppose they have given like this: as per the experimental data, A plus B is gives rise to some P, then what is the order of the reaction? The order of the reaction as per the rate law, here I am indicating K into A into B, then the order of the reaction will be also once again 2. Why? Because sum of the powers, this is the according to rate law, right? So here you can not take the order of the reaction by theoretical expressions, but don't expect the order as every time it is equal to the sum of the powers. Actually this order can be calculated by experimentally, not theoretical. Clear? So as per the experimental data, first of all we have to calculate rate law, and based on that rate law we have to calculate the order of the reaction. So this is, I am assuming this is the experimental rate law. So based on this I am calculating the order of the reaction. Suppose an example, they have given a equation 1 by 2a plus b is gives rise to p. As per the rate law, they have given like this: k into a power 1 by 2 into b. Then what is the order of the reaction? Now what is the order of the reaction? Sum of the powers, that means 1 by 2 plus 1. So order of the reaction will be 3 by 2. So this order may be fractional. This order may be fractional. That depends upon experimental data, right? So order may be fractional, or may be a whole number, or may be a whole number, or may be a zero. Clear? So order may be zero or a whole number or fractional. Clear? So based on the experimental only we have to calculate the order of the reaction. Now we need to calculate the rate constant units, the rate constant units based on the order, based on the order. Suppose example, you need to calculate the rate constant units for first order reaction. First order reaction. What is meant by first order reaction? That means order of the reaction is 1. The order of the reaction is 1. Let us assume a reaction is gives rise to products, right? So as per the rate law, I am writing R equal to K into A to the power of 1. Clear? Now as per the rate law, we have to calculate the K units. So from this I am writing separately K equal to R divided by A to the power of 1. And we know that the units of rate constant, the units of rate of reaction, that is mole per liter per second. Clear? So here I am writing a short form: mole per liter I am assuming as C, and the seconds I am assuming as with a T. Clear? I am always using this expression now onwards in order to calculate the units in a easy method. Clear? So now here I am substituting where concentration of A once again. So concentration of A is nothing but mole per liter. So you can calculate directly here: mole per liter get cancelled. We have got 1 by second. That means second inverse are the units of first order rate constant. Clear? And in some books you may get as like this: mole per liter we can indicate by C by T, right? And whole divided by once again mole per liter, that will be C. So C by T into 1 by C, CC will be get cancelled, and we have got 1 by T, that means second inverse. So you may use this method or directly units method. Clear? So this will be the units of rate constant for first order reaction. Similarly, you can calculate for the second order reaction. For second order, what are the K units? Very, very important, right? So once again, I am assuming a reaction like this: 2A is gives rise to product, and as per the rate law I'm writing as r equal to k into a to the power of 2, right? So now I have to calculate about the units of k, that I'm writing as the expression r divided by concentration of a square. So as already just now we have discussed, where r equal to I'm writing mole per liter per second as c by t. Therefore here I'm writing mole per liter, where a is concentration, that means mole per liter. Mole per liter I'm writing as c, so here square will be there. So upon simplifying, c by t into 1 by c square, where I already indicated that c, where c is nothing but mole per liter, where time is nothing but here seconds. Clear? So now upon simplifying, here c square will be there, get cancelled. So we have got 1 by c into t. That means 1 by c nothing but 1 by c nothing but liter per mole, that means liter mole inverse, liter per mole, that means liter into mole inverse into 1 by t, that means second inverse. So answer will be the liter mole inverse second inverse. Clear? So these are the units of k for which order? Second order. So like that you may calculate for zero order, for any order. So generally I'm writing the nth order. So suppose I'm taking for a nth order reaction. So as usually I'm writing the rate law as r equal to k into a power n. Now we need to calculate k, that means r by a power n. So I am going to deriving a general formula, right? So no need to calculate every time first order second order, right? So generally you can take a formula to derive for any order rate constant units. Clear? So r equal to, just now I have explained, I am taking c by t, and here it will be c power n. That means c by t into 1 by c to the power of n. That means here c power 1 minus n, right, into 1 by t, into 1 by t. That means I'm writing as directly second inverse. Clear? So you can expand where c as mole per liter whole per whole to the power of 1 minus n second inverse. So this is the general formula for any kind of order of reaction. Suppose if you want to calculate for n equal to 0 order, n equal to 0 order, so therefore you can substitute n equal to 0, right? So n equal to 0, upon putting n equal to 0, we will get 1 minus 0 is nothing but remains same 1. So therefore answer will be mole per liter into second inverse is the rate constant unit for 0 order. Similarly, you may substitute n equal to 1 to get first order rate constant units. So obviously 1 minus 1 will be 0. So anything power 0 is equal to 1. Therefore, you will get 1 into second inverse, that will be second inverse. Clear? So learn the general formula. Remember this in order to calculate any kind of order of reaction rate constant units. Clear? So this is what the about the rate constant units. Now let's see some questions how they will ask in examinations. Suppose they have given a question like this: for a reaction, for a reaction rate constant is 0.693 second inverse. Then find the order of the reaction. Find the order of the reaction. Clear? They have given the options like 0, 1, 2, 3, which order it is, right? Now let us, here you need to observe the rate constant units. So they have given only about the data of rate constant. Clear? So rate constant units, based on the rate constant units you need to identify the order of the reaction. Just now we have discussed the second inverse is the units of first order. Clear? So therefore answer will be second option. Clear?